Well, dear students, we are now going to start 29th lecture in the series of mechanics of metal forming. If you recall back the previous lecture 28, wherein we took certain example based on upper bound formulation, and the last one that we took a situation, three-dimensional situation, but it was limited to a case of axisymmetric extrusion problem, cold extrusion problem, and the solution was suggested for average extrusion pressure based on a streamline function, where so we have seen that we started with the kinematically admissible velocity field, but because the die surface was having a die profile that was given by a equation, that was Rz. So and that's how the requirement of kinematically admissible velocity field was automatically satisfied. Now in this lecture we are going to take another a much complex upper bound solution for generalized 3D shapes, and that is how it is a real life problem, but we have restricted it to cold extrusion situation again. So when we take three-dimensional generalized case, so this solution would give for any shape, and therefore the whole shape, the whole class of extrusion shape can be classified in two major category. One as the one a simple, and the another complex, and complexity depends on a complexity factor that we would explain later. So generally as far as the dies are concerned in extrusion, we come across continuous die and square die. As the square dies are used in hot extrusion, whereas continuous dies are used for cold extrusions. The continuous dies may further be divided into two categories. The first category that consists of streamlined die, and that is the streamlined continuous dies. For an example, it is a third order, fourth order, fifth order polynomial dies, cosine dies, etc. Whereas second category the encompasses the conical dies, hyperbolic dies, elliptical dies, Blazinski's, that is CRHS, that is the constancy of successive generalized homogeneous strain increment, that is called as CRHS, and then modified CRHS dies. These are some of the dies one can see in literatures. So the HS dies are constructed in such a fashion that it minimizes the internal power of deformation, that is IPD, but there are lower power and lower losses at the entry as well as exit section because due to discontinuities. So, it has been found that the first category of dies require comparatively less amount of power for extrusion in cold situation, and the extruded products due to uniform deformation have absence of intensive shear bands that results in better microstructure and mechanical properties. However, the second category that we discussed of the dies are also preferred as a conventional practice, however. So, despite the increased demand for 3-dimensional extrusion of generalized shape section through continuous dies, so far very little systematic has been done, and that is how I thought to tell you this case also, which is a generalized upper bound solution. And this solution, because it is a upper bound 3-dimensional and it is generalized in nature, so it can be simultaneously used for designing the extrusion process for any situation, and especially cold. It can also be linked with hot situation as well. So, as I told you, whenever any upper bound solution is proposed, first the constitutive equations are very much useful for proposed upper bound solution. So, this particular model that we are going to start with, the upper bound, it is based on construction of, therefore, the kinematically admissible velocity field that consists of straight or curved streamlines. So, estimation of extrusion power for cold extruded component shape with strain hardening material is based on a segmentation concept that is introduced, and it is in fact derived from a pseudo vortex concept which was proposed few years before by our group of research work. So, this particular the pseudo vortex concept and related issue segmentation concept, when added with upper bound solution that we are going to tell, it can be applicable for both re-entry case and non-re-entry case, because the whole shape, whole class of extruded shape can be classified into one which is called as non-re-entry shape and another is a re-entry shape. We would let us see what is non-re-entry shape. Suppose you take a closed boundary, any closed area, and which may be a extrusion shape, and if you take the centroid of that, and from centroid if you draw a line which is radially, and now if you take this line and let us rotate around this shape, this closed shape. So, you will find that this line which is starting from center line and it will be cutting through the boundary of this shape, will have everywhere it will have only one intersection. So, if the shape is such that there is, when you move around the whole object from the centroid, this line or ray, then if it is only one intersection, that shape would be called as non-re-entry. If there are two or more than two intersection at any point at any angle while rotation, then it will be called as re-entry shape. So, this concept has to be first very carefully understood. So, we would be first start with non-re-entry shape components. So, let us first start the basic constitutive equations that would be used. So, because this case is supposed to have a steady state forming process of extrusion, cold extrusion. So, and even these constitutive equations can be applied for drying, rolling, etc., all the processes. So, the measure of deformation is basically for any of these processes is in fact strain rate tensor, that is epsilon ij dot. So, as you know, the strain rate tensor can be shown by this equation, that is epsilon ij dot is equal to half of the deva vi divided by deva xj plus deva vj divided by deva xi, where vi and vj's represent the velocity component along xi and xj direction respectively. So, in order to express the constitutive equation in a much convenient form, the stress tensor, that is sigma ij, can be decomposed like in two parts, as the derivative part and as the hydrostatic part. So, that becomes sigma ij is equal to sigma ij prime plus p delta ij, that is the canonical delta, and where p is minus sigma kk by 3, that is the hydrostatic part. So, in bulk metal forming processes like extrusion, drying, rolling, etc., the total strain are large as compared to the elastic strains. Therefore, the elastic deformation, if it is can be considered as negligible compared to the plastic or plastic deformation. So, the constitutive law for rigid plastic material, so we would be taking the material as rigid plastic here, and that the equation, constitutive equation that relates the derivative stress sigma ij prime and the strain rate, that is epsilon ij dot, can be written as this equation, where so that means sigma ij prime is equal to 2 nu sigma epsilon ij dot. So, nu is your in fact Levi-Mises coefficient, we call nu here, not nu, it is not similar to the coefficient of friction we discussed earlier. So, here nu, which is defined as the ratio of generalized stress divided by 3 times of the generalized strain rate, this is shown here. So, this yields the von Mises criteria. If and let us assume that whatever deformation now we are going to deal, it obeys the von Mises yield criteria. So, using this Levi-Mises coefficient, that is nu, the generalized stress, as you are aware, it is the under root 3 by 2 sigma ij prime that is the tensor form. So, and similarly one can it is known that generalized strain rate is 2 by 3, that is under root 2 by 3, and epsilon ij dot and then using these two, the generalized strain, that is epsilon bar, can be calculated from generalized strain rate. So, that is nothing but the integration over from 0 to t generalized strain multiplied by dt, where dt is the time increment, and we would explain, that is dt is again the ratio of velocity divided by the other length, we would explain. So, in fact the generalized stress depends on generalized strain rate and temperature in the process, but because this is the case where we are dealing with the cold extrusion at room temperature, so the effect of temperature on generalized stress can be neglected, and then simply one can write down the generalized stress equation which would be suitable here. That is the functional, that is the generalized stress is equal to the functional of generalized strain and strain rate only. Temperature is neglected there because. Now look at this figure number 1, where the deformation zone and the typical streamlined surfaces in the extrusion is shown. Now this is a generalized one here. So you look at here the S1, S2 and S3 surfaces, and you can recall back the previous also lecture. So S1 is the entry where the billet enters through the surface S1, S2 is the exit, the extrudate comes out, and S3 is the die surface, that is the S3, and that is here again it is a streamlined. Streamlined means the each particle follows this path which is defined by Fz. So Fz can be any value, and let us see that V0 is the initial billet pushing velocity, and the diameter, initial billet diameter is R0, round billet is generally used, and this is what is the another streamline which is shown depending on the extrusion ratio at the entry and exit, because the extrusion ratio is constant, so it will maintain at S1 and S2 side, and that is how it is if any other streamline is chosen. So let it to be xi R0, and on then the other side, exit side, the product average diameter, if it is expressed as Rp, it is Rp, and then corresponding the other streamline exit is xi Rp. So this is what is the situation, and please note that the OI direction and OZ direction and the entry cross section is generalized, entry cross section is circular, but the exit cross section is not circular, it may be any shape depending on the die profile which is here. So if we now propose the upper bound formulation for this case, so one has to assume a kinematically admissible velocity field, so which is quite close to actual velocity field. So another distinguishing characteristic of the upper bound model is that the kinematically admissible field is expressed in terms of Cartesian coordinate system for streamlines. So we would be, because now choosing a streamline, which makes it easy to incorporate variable yield stress. So the proposed model that now we are going to deal is appropriate for generalized non-re-entry safe extrusion through a fairly general class of die profile. We would see the different die profiles as I mentioned: conical die profile, streamlined die profile, cosine die profile, hyperbolic, elliptical. So these could be. So the function Fz, it could be anything. And if you recall the very old work, 1959 work by Prager and Hode, they proposed the basic upper bound theorem long back in 1951. So that states that among all the possible kinematically admissible velocity field, the one which minimizes the total power, that is here whatever it is given here in equation, this total power, that is the summation of two things, that would give the upper bound value. So, let us start with, so starting with this and remembering the figure 1, let us make certain assumptions. There are certain assumptions that we are going to make it, and that would be valid for throughout the analysis which are now going to start. So, this assumption number 1 is that the material is incompressible, it is rigid and perfectly plastic material, but it follows certain strain hardening curve. Please remember, earlier two cases we did not took any strain hardening, and that is how here generalizing now we are considering some strain hardening curve. Secondly, second assumption is that the deformation takes as a homogeneous deformation within the domain of the deformation, and it is steady state conditions are there. So, homogeneous and steady state. Initially it may be slower, but and then somewhere it may be decreasing, increasing. It is not like, we take it as a homogeneous deformation and steady state. Third assumption, that the deformation zone is assumed to be bounded by straight plastic boundaries at the end section of the die. As I explained, the surface S1 and S2, it is straight. In fact, many people have considered that it has certain curve, but therefore in this particular assumption we take that the deformation zone, and particularly the zone S1 and S2 in figure 1, is assumed to be bounded by straight plastic boundaries at the end section and at the exit section of the die. The fourth assumption is that the neutral line is the line that joins center of gravity of the billet, as I told you. That is, if you look at the figure where earlier figure 1, that is the point O, and the CG of the extruded product that is at point O dash. So, if you look at this figure number 2, so at this figure number 2, this is O and this is O dash. So, you see the OX, OY, and here when there is a 3-dimensional figure is shown here. So, this is what the situation. The fifth assumption is that the stream surface, if you look at this figure, the stream surface, especially OE, E dash O, it consists of a number of predefined streamline, straight or curved. So, if you look at this figure where OEG on the billet side and O dash, E dash, G dash, it is, and F dash, it is on the. So, here two streamlines are shown. So, streamline EE dash and another is shown as F dash. So, these are to be. So, from the center O, the OE length is R0, and any other streamline which is taken as its length could be N. So, it can be anything. So, this is what the fifth assumption. So, that means it is a number of predefined streamlines, straight or curved. The sixth assumption is that the particle that passes through an arbitrary point F, which is shown here in figure number 2. So, on line OE, it goes towards the corresponding point, that is F dash, on the line, that is O dash E dash, maintaining the proportionality of position. So, this is what is the sixth assumption. Seventh assumption, that the elastic strain is small and can be neglected, as it is the very basic initial we started with. The last assumption that could be, in the present analysis, because the friction factor between the die and workpiece is concerned, so it is assumed that it is independent of slip. So, there is no slip, and it is also assumed that the friction factor is constant throughout. So, if you see the figure again here, so now you take this center line, the center of gravity, that is OO dash line. You see the flow of the material is from right side to the left side. So, from the right side it is the entry, and left side is the exit, and you note down the shape of the 1/4 of the billet is round, and here on the shape, a given shape which is not round. So, that is the situation where the geometry of the die and streamline is shown in a 3-dimensional very peculiar and complex shape. It could be anything. So, if you look at OO dash, that represents the direction Z. So, if we calculate the velocity Vz, it would be along this surface, that is S1. The surface S1 means that is corresponding to the entry side. So, the velocity is V0, if you recall. Similarly, the Vz would be V average at the exit side, that is the surface S2. Why I am saying it as V average? Because the velocity in fact will be at any point at the exit side will be different. So, I take the average of all those velocities, and that is how it is written as V average. This is for convenience, but later we would understand what is the meaning of V average, and that is how the V average is defined here. The I summation over I is equal to 1 to summation over n, Vi divided by capital N. If suppose at the exit side there are n number of points, so the velocity of each this point at the exit cross section would be Vi. I can be from 1 to n. So, let us sum up all those velocity and take the average. That is how it is kept divided by n. And please note that if the OO dash is the neutral line, that is would be representing as the neutral line. So, this neutral line, if I say the velocity is Vn, it should be equal to 0, because neutral line is unaffected. And one more thing to remember, that O dash G dash, if we take the O D dash on the product side, that here it is taken as A1. Let us take it as A1, and similarly O dash E dash, which is, and it is taken as O2. And one more thing is that there is an angle between, as on the exit side, that is between angle G dash O dash E dash is xi, and on the billet side the angle between GOE is phi. These are to be remembered. And if you take this length, that is G dash E dash on the product side, it is a straight line, always a straight line. This is another assumption that I could have explained earlier. So, this assumption that G dash E dash is a straight line always. So, you choose such a small angle psi that results into, and this is what is called as slicing. This is the what is the slicing concept. The whole 3-dimensional geometry is sliced into such number of slices. So you slice is like this and all around. So this is what, and therefore the surface of the slice, bound outer surface, is always a straight line. It is no more curved depending on the geometry. It is no more curved, but it is a straight line. That is how it is. A very fine slices are taken. So that is the assumption. So if you recall this figure number 2, the extrusion ratio, that is from whatever reduction takes place. So extrusion ratio, one can define it as that is the area of triangle O dash G dash E divided by the cross sectional area on product side, and that must be equal to the area of triangle OEG divided by cross sectional area on the billet side. So that is how these two sides must be equal. And if you see the coordinate, if I take the coordinate of G dash and E dash, so G dash coordinate and E dash coordinates are x1 y1 and x2 y2 respectively. So if the angles xi and phi are there, so that means cos xi is equal to b1, where b1 is b by a1 multiplied by a2, where the b is taken in the form of coordinate as, which is equal to x1 x2 plus y1 y2. That is how, and therefore sin xi, that is the sin xi, can be calculated as phi capital A divided by pi a1 a2. Capital A is the cross sectional area of the billet. So the streamline, now the streamline geometry is chosen it like this. So because it has a 3-dimensional streamline is, so the let us take the streamline formula or the geometry as, that means x part as f1z, and that is equal to b1 z power 4 plus b2 z power 3 plus b3 z power 2 plus b4 z plus b5, and similarly y is f2z, that is c1 z power 4 plus c2 z power 3 plus c3 z power 2 plus c4 z plus c5, and z is z because now we have taken the geometry in 2D situation. So z is z, and if we now impose the boundary condition at the billet side where z is equal to 0, as well as at the product side where z is equal to L. Capital L is taken as the length of the die, because this geometry which is shown here, it is in figure 2, it represents the die portion. So that is how the total length, that is the OO dash, is capital L. This is the total deformation zone. So this particular deformation zone is this as shown here in figure 2. So if you impose the boundary condition at billet side at z is equal to 0 and at product side at z is equal to L, so at billet side would be, that means x is n sin phi and y is n cos phi. This is first boundary condition. Second boundary condition is that derivative of, that is the deva x by deva z with respect to along the z direction is equal to 0, and deva y by deva z is also equal to 0. So these are the two boundary condition at the billet side, and similarly on the product side x would be equal to n a1 sin y sin phi divided by r0, and y is equal to n A1 cos psi by R0, and the second condition on the product side is, that is deva x by deva z is 0 and deva y by deva z is also 0. So, using these 4 boundary conditions, rather no, the 4 boundary condition on the billet side and 4 boundary condition on the product side, total 8 boundary conditions are there. So, if we define the capital C value as AA, capital AA divided by pi A1 A2 cos xi. So, if we now substitute these things in the previous equation where we defined the streamline, 3-dimensional streamline. So, now it can be shown here, that is the equation. So, that means x is equal to n sin phi plus n multiplied by phi A1 by R0 capital C minus sin phi, and multiplied by the function of the, that is the geometry of the die, and that is Fz. And for this case where the streamline is chosen, that represents a fourth order geometry. Similarly, y and z is written here. So, if we substitute the other things from the previous equation, so if we now put, that is this is what is Fz. So, Fz is the die profile. So, that is Fz. Now, if we replace, so this equation simplifies here. So, where Fz is 0 at z is equal to 0, no doubt, and Fz is 1 at z is equal to L. So, these boundary condition would always be satisfied to boundary die profile. So, you can choose any die profile Fz in such a manner that Fz is 0 at z is equal to 0 at that means at the entry, and it is equal to 1 at the exit side. So, using these boundary conditions on the deformation zone and on the die profile, now one can write down the Jacobian matrix. So, this is what is shown as the Jacobian of these equations. So, now you can see the Jacobian J, it is having 9 components, mainly the so first like the x by n, y by n and 0, and this is what the second term, third term, and this is a long Jacobian and it is a complicated Jacobian which is calculated based on this definition of the, where it incorporates f. So, f is nothing but Fz, and Fz for this case is fourth order die profile, that is 4 z by L cube minus 3 z by L power 4, that is the simple die profile. So, one can determine the determinant of this Jacobian, one can very well find out the determinant. So, if we calculate the determinant of this particular Jacobian, so it can be written as det j, that is determinant j, and that would be equal to n g, g is a function of phi and z. So, that is det j n multiplied by g phi z, where g is a function, that is g phi z is a function, it is a long function and it has been shown here. So, that is a 1, 2 and 3 major summation. The first summation is 1 minus f square plus c a1 by r0 f whole square. Second summation is 1 plus c multiplied by 1 minus f multiplied by a1 by r0 f multiplied by cos phi, and the third summation is multiplication of two things, that is c multiplied by 1 minus f multiplied by a1 by r0 multiplied by f multiplied by f sin phi. So that is what's the whole Jacobian defined. Because the volume continuity, because of the volume continuity, the velocity components along z direction in the Cartesian coordinate system is Vz. So it should be V0 at the entrance, as usually I told you, and it should be equal to Vf at the exit site of the die. So V0 and Vf are the speeds of the billet and the outgoing product respectively. So Vf can be determined by this equation. So Vf can be determined as the numerator as pi multiplied by r0 square multiplied by phi by 2 pi, and denominator as half of a1 a2 sin phi, and the whole multiplied by V0. So this is a very simplified equation of the volume, and that satisfies the volume constancy as well. Then this using Vf, now one can derive the component of the velocity like Vx, Vy and Vz, because it is a 3-dimensional. So the Vx, Vy and Vz is given here, that means Vx and that is all in terms of V0. So Vx becomes n multiplied by a1 by r0 c, capital C, which is defined the value of C earlier, multiplied by phi minus sin phi multiplied by f prime z. F prime z is the derivative of die function, that is the die profile f z, and divided by g phi z multiplied by V0, and likewise the y component and z component is shown here. So using these three equations, that is the velocity field which is given by these three set of equation for Vx, Vy, Vz, it is found that the velocity boundary condition is fully satisfied, and the strain rate therefore can be evaluated using these equations. So the partial derivatives of these equations can also be found out with the help of coordinate transformation, and the transformation that is used here, it can be used here. That means deva Vi by deva xk is equal to summation j is equal to 1 to 3 multiplied by deva Vi by deva uj and multiplied by deva uj by deva xk. So this term, that is deva uj by deva xk, is inverse of the Jacobian which is expressed earlier, Jacobian. So using the previous equations, the expression for components of the strain rate can be obtained, and because this component is long enough, so I am not giving here, but this reference is written for your information. So you can note down this in reference, and this work is already published earlier. So you can see the details of the component of this strain rate, and then you can understood the peculiarity, the very long format of the component, 9 component comes, and then based on this, then here is the value of dt which is defined as dz by vz, and therefore the generalized the strain can be calculated as integral of generalized strain rate divided by vz dz, and this integral of the generalized strain, in fact it is performed using point Gauss quadrature rule to find the cumulative generalized strain along streamline. So once the generalized strain is calculated along the streamline, which is cumulative, then it can be further calculated as the stress, corresponding stress at every point. So now with this equation we are able to get the generalized stress and generalized strain at any point across the streamline, at any point across, and this will help us to further explore into. So let us see then how to calculate or estimate the extrusion power and average ram pressure therefore. So let us look at this figure again, number figure 2, and let us take one such element. So we are taking one such element, that means element OE G G dash O dash E dash E O, and this is what has been shown here in figure 2. And if we say the total power, that is this total power, which is marked as subscript as capital T, which is consumed within this element, can be written as the summation of this. So the total power is the summation of the internal power because of the internal deformation of the material, second the discontinuity power of deformation at the entry section, that is E denoted, and the power that is consumed at the exit discontinuity of the surface at the exit side, and F represent the power as the die surface interface friction. So the total power within the element is therefore the sum of these powers, that is the plastic deformation power, the velocity discontinuity at the entry and exit of the die, and the frictional power loss along the interface between the material and the die. The predicted work power, total power, which is obtained through the present velocity field which is proposed, would be higher if no other redundant power losses are there. So that the power actually any other power that is actually consumed. So each power in the power element is computed numerically using velocity, strain rate components that we have just proposed, the generalized yield stress which is based on the generalized strain, yield strain of the material, and the given friction condition. So now look at this figure number 3. This is what's the other slices. In the figure 2 only one slice has been shown in the 3D way. This shows the 3-dimensional all the slices. So you look at, this is the billet side, and this is what's the a very peculiar geometry of the product that has to, and when you join this streamline from the corresponding point at the billet side and at the exit side, that is you can now get the streamline. So this is what the, and you note down the different angles on the billet side, that is phi 1, phi 2, phi 3, phi 4 and phi n depending on the number of slices, and the xi 1, xi 2, xi 3, xi 4 and xi n on the product side. So this is what the construction of power elements for a general non-re-entry shape. So this is a general one in the sense, and this is a non-re-entry. Non-re-entry I explained in the very beginning as if this is the center of gravity of the shape and these are the lines. So you will see this particular case is a non-re-entry because everywhere there is only one cross section, nowhere. If you take the example of H, so that you will find that somewhere it is more than 2 intersection. That is how H section, T section, etc. are treated as a re-entry shape. So, this has to be noted here. So, then we can calculate the total power. So, this total power, the internal power of deformation will have a 3-dimensional integral, that is the this is the triple integral, and it is given as 2 by root 3. Sigma generalized stress must be inside, actually it is inside. So, this is generalized stress, and multiplied by half of generalized strain rate Ij and generalized strain rate Ij under root, and this is mod of det J, dn, d phi and dz, because the n, phi and z has been explained earlier. So, and these triple integrals corresponds to 0 to capital L, 0 to phi and 0 to r0 across the, and that is why this is the 3-dimensional domain, right. So, this becomes the internal power of deformation, and then the frictional power of deformation is at the geometry of the die. So, this is given as m generalized stress by root 3 and multiplied by the double integral Vx square, Vy square, Vz square at the r0 entry, n is equal to r0 under root, and 1 by cos alpha multiplied by d deva xz divided by deva phi z d phi dz. This is what the frictional, and the alpha, what is alpha, it has been explained here in the on the next slide. So, alpha is determined the position of the a point on the surface of the die and its location with respect to the within the domain, and similarly the shear power is calculated as at the entry side as this one, that is sigma 0. Here in the frictional power and internal deformation power, generalized stress is used, but here in shear, because it is entry and exit, your the sigma 0 is used, that is the yield stress of the material without strain hardening, because initially there is no strain hardening. So, that is how it is taken as 0, and therefore, it is taken as like here. So, this becomes, and at the exit side is this equation. So, if you sum it up the whole thing, for one slice one can calculate the total power, that is what has been shown here in this, that is the phi t is psi I plus psi e plus phi o, that is, and phi f. So, that is how so the generalized yield stress at any point, as I told you, can be calculated using the value of generalized strain rate strain at that particular point. So, the value of this in the deformation zone is obtained by integrating, as I told you, the generalized strain rate along the streamline. Now you look at this figure where the broad image of the slices are shown. So, if you look at the definition of 3 more angle as delta angle, alpha angle, and this is as zeta angle. So, and LL is the length of the diagonal. of the small unit square element on the die surface, and that can be calculated as LL under root cos delta square plus cos gamma square. So that is the gamma. So you look at this, this is delta angle, this is the angle alpha, and this is the angle gamma. So these are angles are to be very it should be understood, because there is a small square element at the die surface, and when the die moves from entry side to there, so this surface is it is changing at every point. So the coordinate of in this figure number 4 has been shown here, like E1 dash, E2 dash, E3 dash, E4 dash, E5 dash, it is easy, and this is what the simple. And similarly E2 and all those things, E7 dash, E8 dash, all those things has been explained here. So the angle alpha, it is subtended by LL with Z XY plane, and it can be calculated as cos alpha, which is equal to LL by root 2. One can see here from there. So a small enlarged view is shown here at this figure 4. So therefore the overall power, that is, if I say at the phi t was for one slice, the total power for one slice. If I say overall power means if for all there are number of n number of slices, so for each slices of this in n slices, now if you add the power, that is phi t1, phi t2 and all that, so that the overall power would be taken as phi 0, phi o is overall. So is the sum of the power, that is phi t1, phi t2 etc. So which is consumed in the various power element of the shape, and this is what the called as the slicing concept in the beginning I told. So from the overall power, that is phi o consumed during the extrusion, the upper limit of the average ram pressure, that is P average, and the relative forming stress, that is R S for the extrusion can be calculated. That means P average is the ram pressure, is nothing but the overall power divided by pi R0 square V0. This is what's the P average, and the forming stress, that is RS, is P average by sigma 0. This is what's the popular equation. So in this case we have taken 6 dies, if we can take. So that is the FZ. So we would take the 6 different types of dies shape, that is FZ, for different profiles, and it can be represented by a third order polynomial die, that is FZ is 3Z by L square minus 2Z by L cube, that is the third order. Fourth order similarly, fifth order similarly, and likewise. And cosine die Fx would be 1 by 2 1 minus cos pi Z by L. Elliptical die would be, for that Fx would be 2 Z by L minus Z by L square. Similarly, the conical die would be, for the Fx, for the conical die would be simply Z by L, because the variation of overall extrusion power, that is phi o, with die length, along the die length is unimodal and is smooth. So the variable interval golden section search algorithm is used for determining the optimal die length, that is L opt OPT. So, this integral, that is the 4 integral discussed previously, it is evaluated numerically, as I told you, using the numerical techniques, and then everything is solved, calculated in the fashion which is explained here, and then one can evaluate the P average and RS, that is the die stress. The whatever has been explained, we would be continuing in the next lecture as well. So, we would see further. It will take 2 more lectures to see the all aspect of the 3-dimensional case. So, I thank you for all for your patience, and hopefully we would meet again next time in the lecture 30th, and by the time you please revise it again, so that we remember the whole equations, all equations, the derivation of this upper bound 3-dimensional generalized case. So, thank you very much.